Hello everyone and welcome to MTC 2023 presentation. My name is Jaideep Bangal. I'm a director at Altair, leading the team of experts focusing on simulation-driven design and manufacturing. In today's presentation, we'll talk about challenges in additive manufacturing. We'll talk about how engineers are using this method in the real world. We'll talk about DFAM, design for additive manufacturing. Also talk about artificial intelligence in computational engineering, and most importantly, want to talk about what's next for the engineers. To start with, there are many challenges when we print the parts. You know, I have seen customers, users printing like 10 to 20 parts before they get one successful good part from the 3D printing. There can be challenges as simple as a bad surface finish, as you see on the screen, or it can be catastrophic failure, like where multiple layers misalign or snap, maybe because of the tensile residual stresses or thermal stresses induced during the printing process. Now, another thing you'll notice on the internet, on the many presentations, there are beautiful designed additive manufacturing parts, like one on the screen. But no one really talks about what it took to print that part from printing side to the support generation. This is another good example. Beautiful part, but the way it was printed, which was designed, it was just very difficult to clean up the part post processing. This was a Bugatti's brake caliper. It's okay, someone can afford to clean up that part, print that part for a car like Bugatti, but not for general purpose production usage. Now, if you can guess what that number is, that's the amount of wastage associated during the printing process. That wastage comes from maybe the material wasted printing supports. Maybe it's a post processing time that's required by an engineer. Maybe it's a powder wasted during the printing process. You know, if we can reduce that 40% cost to zero or at least minimal, the additive manufacturing can become affordable. Just to give an examples of some of our users in the industry, this is an example from the heavy industry how they are using these tools from designing parts for specific additive manufacturing process. In this case, it was a Selenium or the binder jet process. Um, I'll give another example of typical manifolds. The whole entire weight was reduced when it comes to 3D printed part at 85%. So this part is not just 3D printed as a block, but it was redesigned such that internal channels will not require any support structures. Few other examples are very good when it comes to implicit geometry lattice structures such as heat exchangers, manifolds, the sports applications such as helmet, and these are very good examples for lattice structures. Let's talk about a few more examples how people are using these tools, implicit modeling, lattice structure, and the additive manufacturing as molding the toolings for injection molding, die casting, manifolds, as we just saw, implants in the medical industry, hip implants, spine, knee. Heat exchanger is another good example for increasing the surface area for good thermal characteristics or thermal performance of the heat exchanger, and the sporting events to reduce the weight or um, increase the performance, improve the performance of the tools. Now, what is DFAM? That's let's talk about DFAM, design for additive manufacturing. So there are two ways engineers design the parts. One, designing something from scratch with a napkin sketch, starting with calculating numbers on a piece of paper or computer these days. Um, and the another way is reinventing or reusing existing design. So let's say this design for in this particular bracket is there for last 10 years. I want to change this design to make it lightweight, maybe use different material, maybe use different manufacturing process, or simply improve the performance. The first step when I design a part is to assess how this part performs today as is. So I'm running a quick baseline simulation. Once the baseline simulation is done, I will create something called design space, packaging space. It's the largest possible area available for engineer to design a part. And from there, when we capture the loads, those loads can be captured automatically running a quick motion kinematic simulation. Those are my worst case scenarios. And from there, a tool will come up with the most optimal design or free design we call. It may not be the most manufacturable design, but it's most efficient design. So at that point, I can go back to the design board, to my design packaging space, and tell the tool to give me a design for a particular manufacturing process. Maybe that process can be casting, machining, injection molding, or additive manufacturing. And depending on my requirements, the tool will come up with a new design good for any of these manufacturing processes. Now, before I do anything with this new new design, I want to run quick manufacturing feasibility check. For example, in this case, if I want to print this part, I want to find out if this part will deform while printing. If it deforms too much in Z direction, that's a given decoder accident or if it is there will be thermally induced stresses, the layers will shift, and that's again the part will fail. If I'm not happy, I can go back to my design side and make changes to the either to design or the process parameters during the 3D printing process. And once I'm satisfied with my printing process, I can quickly run validation, FE analysis. Now I change the design. So I want to run a quick validation step to make sure my new design satisfy my design criteria that I started with earlier. And if everything looks good, then I can send this part for the manufacturing. So this completes the entire cycle for my design to manufacturing. In this case, design for additive manufacturing. But that said, Inspire or Altair solution is totally neutral when it comes to manufacturing process. Now, the tool can come up with a design which is good for conventional casting, machining. It can be powder bed, laser melting, sand molding. I call hybrid printing, where you can print the sand molds and then use casting as a manufacturing method. You get best from both the worlds, where you get complexity, lightweighting from 3D printing, as well as you get casting or the good material properties, proven material properties from the casting as a manufacturing process. Machining, FDM, or it can be metal binder jet process. So now, saying that to achieve this, we have a multiple simulations tools for manufacturing feasibility check for casting, metal forming, injection molding, extrusion, both for metal and polymer, additive manufacturing, and polyurethane forming. The idea for using these tools for manufacturing simulations, FE analysis, as well as optimization is to detect failures very early. Not only detect, but now fix those failures or issues during the design phase. Don't wait uh, for something to go wrong at the end of the products. Let's look at how this process really work. So let's take I have an assembly of the this is a rear suspension for one of the bikes, super bikes. This middle part I want to redesign. So I run a quick motion simulation, kinematic simulation, capture the loads on joints and parts and so on, and I define this as my design space. And the tool then comes up with the most optimal flow path for a given manufacturing method. In this case, it's a laser powder bed fusion method I selected. And once the design is done, I can calculate or capture the geometry very quickly, uh, create a final CAD geometry, and then use Inspire Sprint 3D capabilities to generate more support structure. Also, run the orientation optimization, find out the best orientation to print this part. And then once the orientation is done, create the support structure. There are different types of support structures users so one can create. And once the setup is ready, I can run quick manufacturing feasibility, in this case printing simulation, layer by layer simulation, to detect the defects, like the displacement, deformation. I can run an inherent strain simulation to find out those problems. Now, if I find a problem, as I mentioned earlier, I can go back to the design, make changes to the design, or I can change the process parameters, printing process parameters, to make sure that the printing is successful. And finally, I get the part when it's done. Now, remember this part I was talking about earlier, this slide where we had some this we call as a snap lines where the layer shifted, and this part is basically pretty much useless. Now there are two ways I could have done. By the way, I've detected this failure from the printing simulation. We could have avoided this either by changing the geometry. In this case, the easy fix was to make those one of the members thicker, so the cooling rate for all the members or entire cross section on that layer is uniform, and hence we won't get layer shifts. That is much easier fix than changing a lot of process parameters where we or adding more support or less support. Another area to look for, earlier we saw where we saw bad surface finish. The tool highlighted the areas where we might see bad surface finish, which we saw. Again, the fix was pretty easy, changing some angles for the overhangs from 45 degrees to maybe go a little bit sharper and avoid all those issues. In this case, it was a bad surface finish. S- Now, how did we find those problems, especially on the snap lines, which was a disaster? On the left hand image is my design 1 and the right hand image is my design 2. If you look at design 1 and in the middle of the image, those arrows or those vectors show deformation in x direction. So, and those arrows actually go like a wiper blade back and forth, and that's what's making those layers shift or snap. So the new design with thicker members, we get the deformation. The deformation will be always there. We're talking about hundreds of or thousands of degrees of heat generated because of the laser and the cooling pattern. So there will be deformation. The idea here is to control the deformation the way we want and make sure the parts is still successfully printed. Now, on the right hand side, because of the main member changes, the cross section changes, there is a deformation, but that deformation is uniform at just on the adjacent layers, and that's getting us the successful part. So, how do we come up with that idea? Is again run the optimization, run the design, use the design guidelines, design manufacturing constraints within the tool to come up with a design which is printable without no support structure, and finally run the printing simulation for the part. Just to compare between design one, design two, very subtle changes, not much, almost to the naked eye won't feel it, but that made that print very successful. And when we printed this part, we printed 12 parts on one plate with no support structure. So one has to just cut the part off the plate and start do the machining operations such as pin locations, bolt location, and so on, and start using the part for the real application, real product. So this is in nutshell is a design for additive manufacturing. So while designing the part, think about manufacturing process. Think about what can go wrong or what guidelines you need to follow during the design process. The next topic I want to talk about is AI or artificial intelligence in computational engineering, including additive manufacturing and other manufacturing processes. So let's start again with talking about some challenges that we see using the AI for computational engineering. AI algorithms heavily rely on large amount of data to learn and make accurate predictions. However, in additive manufacturing, especially in novel applications or specialized industries, there may be a limited data available. This lack of data can hinder the development and the training of AI models. In some additive manufacturing applications, obtaining a large amount of label training data can be difficult or very costly. For specialized or niche applications, the available training data may be sufficient or insufficient to train accurate and robust AI models. Techniques such as data augmentation or transfer learning or active learning can be employed to overcome the limitations or limited training data. Applying AI to optimize the additive manufacturing process requires defining appropriate objective functions, considering multiple variables, and navigating the vast design space. Additive manufacturing involves a multitude of parameters such as material selection, design geometry, printing parameters, and post processing techniques. Optimizing these parameters for improved quality, efficiency, and performance can be a very complex task. AI models, particularly deep learning models, are often considered black boxes, making it difficult to interpret the reasoning behind the predictions. In the context of additive manufacturing, where material properties, structural integrity, and performance are critical, it is essential to understand why an AI system is making specific decisions or recommendations. Lack of interpretability can hinder trust and acceptance of AI system in safety critical applications. Next is talking about the QA calibration and validation side. Ensuring the quality of additively manufactured part is crucial. AI can be used to develop systems for real-time monitoring, defect detection, quality control. However, establishing reliable and accurate quality assurance systems using AI requires addressing challenges such as limited training data for defect identification, dealing with complex defect patterns, and achieving real time performance. Calibration and variability in additive manufacturing systems including 3D printers, can exhibit variations in performance, calibration, material properties. These variabilities can affect the quality and the consistency of the printed parts. By incorporating AI techniques that can adapt and compensate for these variables is a challenge. Techniques like adaptive learning, online learning, and model updating can be used to address these challenges. Now, scalability and transferability is also is a big challenge. Developing AI models for additive manufacturing that are scalable and transferable across different printers, materials, and manufacturing environments can be challenged. Also talk about the regulations and legal challenges or standardizations of the systems. As AI becomes more integrated into additive manufacturing workflows or any manufacturing workflows, regulatory and legal considerations arise. Certifying AI-driven manufacturing systems may require new standards and guidelines to ensure safety, reliability, and compliance. For that, as a solution, Altair have different solutions to address AI, Altair Physics AI, Altair Design AI, Altair ROM AI, and Altair Rapid Miner. Physics AI is a tool designed to predict physics outcome quickly. The technology leverages historical simulation data to deliver fully animated physics predictions in a fraction of the time it takes traditional solvers to do the same. Design AI combines physics based simulation driven design and machine learning based AI driven design to create high potential designs earlier in development cycles. Reduced order models are a computationally efficient way to incorporate detailed 3D simulations into 1D environment for system level analysis. Altair's Rapid Miner is a data analytics and AI platform which reduces traditional data analytics and machine learning application barriers. Now, in today's session, we'll more focus on the design and the CAE side, which is a entry point to AI for most of engineers. I mean, nothing stops any one of us to get into the next steps, such as test automation, digital twin, warranty analytics, predictive maintenance, quality analytics. It's all there. It all can be used using the tools we talked previously. But today, for today's discussion, we're going to focus more on the CE automation side or design optimization side using Altair Physics AI. So, what is EDS? What is engineering data science? In this case, let's think about geometry, which is a oil pan. The geometry for the oil pan when we run the AI systems, AI models in the background, We want it to recognize the shape, recognize the features. Then using the simulation data, previous simulation data, we want physics field predictions to come up with that. And then also the design generation, right? We want to come up with multitude of designs which um, which we can select from one good design or two good designs to take it to the next step. And of course the user environment, where in this case, the full vehicle system, which can have mm, hundreds of millions or billions of nodes uh, and the predictions to come up with. And how to handle that data is also becomes very important. Let's talk about physics a little bit in depth. If you use hyperstudy in the past, where a user, the engineer, can define the design variables, run the machine learning algorithms, and maybe use assign a scalar factor to as a, there's a goal for the next one. The engineer could have used maybe a design explorer from the HyperWorks. And the last one is the physics AI, which works on the mesh as well as on the CAD geometries, where you can bring the CAD geometry mesh, define the loads, run the GDL in the background, train the models, and finally get the results in very quick manner. So how does it work? Let's talk about, you have all our engineers run the simulations for many years now. We have the historical data sets. We bring the historical data sets, we train the physics AI model, and we get the real-time exploration, design exploration, or the analysis exploration, and then finally we can validate the geometry, the new model. For in this case, it was a flow analysis through the ducts. Um, it can be used for any other method such as forming or stamping as well. So let's look at how it works. This is a real-time physics AI predictions. I'm loading the mesh in this case. Now I'm going to the predict. And it's predicting the displayed model, and we're coming with the pressure drop or the pressure variation in this particular case. The next step to that is we're using the CAD file as a starting point. Bringing in the CAD file, parasolid file. From the parasolid file, again, we go into the, now it's calculating in the background to come up with the different designs. That's our first step, call it in the physics from CAD to contour. Now, how do we train and test the data? As engineers, as mentioned earlier, we have tremendous amount of simulations we have run in the past. We can access those results, use those results to train the AI models for the physics AI models. So in the training part, let's say we have run pressure analysis or the pressure drop analysis on different ducts. So reading those results, in this case, we ran using one of our Altair tools to run a CFD analysis. We are importing that data set. Once the data set is extracted, okay, we can go into the model training part of it. Creating a new training model, called train data, define the entities, what outputs you're looking for. Let's say pressure drop is one of the outputs we'll be looking for, and then run the training models. Next step is testing, or once we have the data, how can we use that data for the analysis or the predicting the analysis? So I'm again going back using this existing data on the new part, and within few seconds, we can get the results back or the predictions back for the new design or the different designs. Now, so what's next? How can we use these methodologies, these techniques we are developing in the real world? Think about large components and think about something as a lattice structure or something as a FE analysis or just in the manufacturing world. Think about you want to run a farming simulations and use your existing simulation data sets to train the models and come up and predict the failures in the stamping. So our team is working with the industries, designers, engineers, manufacturing engineers at various companies. We'd love to talk to you, understand your applications. Maybe we can work together on some of the examples you have and say how these AI techniques can be used. Again, thank you very much. Thanks for attending through this session, and wish the MTC the best luck. Thank you.